In this video, we'll be solving part 2 of exercise 9.3 questions from chapter 9 circles of class 9 CBSE mathematics. In this part, we'll be solving from question number 7 to question number 12. Let's take a look at question number 7. If diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, prove that it is a rectangle. Let us start by constructing a cyclic quadrilateral as explained in the question. So let ABCD be the cyclic quadrilateral, and we know that AC equals to BD because this and this are the diameters of the circle. Now for ABCD to be proven as a rectangle, we need to prove that opposite sides are equal and all the interior angles are 90 degrees. Let's see how to do that. In this figure, if I am considering triangle BAD, that is this triangle, and because I know that BD is the diameter, so this whole arc BAD is nothing but a semicircle, and we know that angle in a semicircle is 90 degrees. So I can write angle A as 90 degrees. Similarly, in triangle ABC, that is the other triangle over here, I know that this whole thing is a semicircle. Similarly, I can write angle ABC as also 90 degrees. Now we know that ABCD is a cyclic quadrilateral. So I can write opposite angles are equal to 180 degrees. So I can write angle A plus angle C equals to 180 degrees. So this angle and this angle, and angle B plus angle D should also be equal to 180 degrees. But I know that angle A is 90 degrees and angle B is also 90 degrees. Substituting that in these two expressions here, I get the value of angle C and angle D also 90 degrees. So we have shown that all these four angles are equal to right angles. Now let us consider triangles ABC and triangles BAD, that is ABC triangle here and BAD triangle here. In this, I know that angle A equals to angle B, which is 90 degrees, and I also know that AC is equal to BD, that is because both are the diameters of the circle. Now AB and AB are the common sides. So from RHS congruency rule, I can say that ABC and BAD are congruent triangles. From this, I can take common parts of congruent triangles CPCT and write that BC is equal to AD here. Similarly, if I consider triangle ADC and BCD, that is BCD and ADC here, I know that angle C equals to angle D, which is 90 degrees, and AC equal to BD because they are diameters of the circle, and CD is the common side here, that is this is the common side. I can say from RHS congruency rule, triangle ADC is also congruent to triangle BCD. From this CPCT, I can write AB and CD are equal sides. So because I have proven that opposite sides are equal and all the interior angles are 90 degrees, I can say that ABCD is a rectangle. 8th question says, if the non-parallel sides of a trapezium are equal, prove that it is cyclic. Let us start by considering a trapezium ABCD where AB is parallel to CD, because in a trapezium, one pair of sides are parallel to each other. Now I am constructing two lines AP and BQ such that BQ and AP both are perpendicular to CD. Now if I consider these two triangles where APD and BQC, where perpendiculars are drawn, in these two triangles, I know that angle APD and angle BQC are 90 degrees. And I know that DP equals to CQ, that is these two sides are equal because perpendicular distance between parallel lines is always equal. Apart from this, in these two triangles, I also know that AD and BC are equal because it was given to me that non-parallel sides of the trapezium are equal. We have taken AB is parallel to CD, so the non-parallel sides are AD and BC. So these both should be equal. So I can apply RHS congruency rule and say that a right angle, the hypotenuse and one side are equal. So triangle APD and triangle BQC are congruent to each other. From this CPCT, I can say that ADC and BCD angles are equal. These two angles are also equal. Now, if I consider AB is parallel to CD and this line AD is the transversal, I can say that angle BAD, that is this angle, plus angle ADC, that is this angle, should be equal to 180 degrees because these are co-interior angles of two parallel lines. Now I know that ADC is nothing but BCD because these two angles are equal. Substituting that, I can write BAD plus BCD equals to 180 degrees. That is, this angle plus this angle equals to 180 degrees. So from equation 2, I can say that sum of opposite angles in the trapezium ABCD is equal to 180 degrees. So according to the converse theorem, if you remember, we can say that if two opposite angles of a quadrilateral are equal to 180 degrees, then it is a cyclic quadrilateral. So I can say that ABCD here is a cyclic quadrilateral. In the 9th question, we are given two circles that intersect at 2 points B and C. So this is one circle and this is one circle, and these are the points of intersection. Through B, two line segments ABD and PBQ are drawn. Through B, we have ABD and PBQ. Two line segments are drawn through these points, and they are intersecting the circles at A, D, P and Q respectively. I have to prove that angle ACP equals to angle QCD. So this angle and this angle are equal. That is what we are supposed to prove. Let us start by considering the chord AP. So I have joined these two lines here and I have considered the chord AP. In this chord, if I take the theorem angle in the same segment are equal, I will get angle ACP equals to angle ABP. So let that be equation 1. Now I have taken the opposite chord, that is chord QC, and from this if I observe, similarly because angles in the same segment are equal, I get these two angles. Angles QCD will be equal to angle QBD. So let that be equation 2. However, in the question we were given that through the point B, two line segments are drawn. So when two line segments are drawn through one point, we know that vertically opposite angles will be equal. So I can say QBD equals to ABP. So from 1 and 2, these two equations QBD and ABP, if they are equal, I can say that ACP and QCD are also equal, proving the question here. In the 10th question, we are said if circles are drawn taking two sides of a triangle as diameters, prove that the point of intersection of these circles lies on the third side of the triangle. Let's see how to prove this. Now, let's construct two circles and a triangle based on the information given to us. So let AB and AC be those diameters of the circles and two sides of the triangles as shown in the figure here. Let the point of intersection be D here. So let's join A to D so that we have two triangles. If you consider the arc ABD, that is this arc here, and the arc ADC here, you can see that they are semicircles because AB and AC are the diameters of the circle. Angle ADB equals to 90 degrees, that is this angle equals to 90 degrees, and this angle is also equal to 90 degrees, angle ADC, because these two here are forming semicircles and these angles are the angles in a semicircle which will always be a right angle. So I can say angle ADB plus angle ADC equals to 90 plus 90 degrees, which is 180 degrees. Here angle ADB and angle ADC here are forming a linear pair, which means that BDC here is a line, which means points B, D and C are on the same line or they are collinear. That implies that D lies on the line BC, which is proving the point that the point of intersection should lie on the third side of the triangle. 11th question says ABC and ADC are two right angle triangles with common hypotenuse AC. Prove that CAD equals to angle CBD. So let's draw these two right angle triangles with the common hypotenuse AC as shown in the figure here. I know that angle B equals to angle D, which is 90 degrees. That's what's given to us because they are right angle triangles. So I can add these two angles as 90 plus 90 and I get 180 degrees. Here I can say ABCD is a cyclic quadrilateral because the sum of opposite angles is 180 degrees. Drawing the cyclic quadrilateral here and considering the chord CD, if I join AC and BD as diagonals, what I will observe is angle CAD and angle CBD are equal because they are angles in the same segment here. The last question in chapter 9 says, prove that a cyclic parallelogram is a rectangle. So I have taken a parallelogram here in a circle where all vertices are on the circle. So it's a cyclic parallelogram ABCD. Let the center of the circle be O here. Here from the properties of the parallelogram, I can write AB equals to CD and AD equals to BC. If I have to prove that this parallelogram is a rectangle, I have to prove that opposite sides are equal, and I also have to prove that all the interior angles are equal to 90 degrees. Here, because it's a parallelogram, we have already shown that opposite sides are equal. Also, from the property of the parallelogram, I can say angle A equals to angle C and angle D equals to angle B, because opposite angles are also equal in a parallelogram. But because this is a cyclic quadrilateral, I can also write angle A plus angle C equals to 180 degrees and angle B plus angle D equals to 180 degrees, because these are opposite angles in a cyclic quadrilateral. From this, I can write angle A plus angle A equals to 180 degrees, because angle A equals to angle C, substituting that here. Similarly, substituting angle B in place of angle D in this equation here, I can write 2 angle A equals to 180 degrees and 2 angle B equals to 180 degrees. Cancelling this, I get angle A equals to 90 degrees and angle B equals to 90 degrees. Therefore, I can say angle C and angle D are also 90 degrees from this expression here, because angle A equals to angle C and angle B equals to angle D. So, I have proven that all interior angles are equal to 90 degrees and opposite sides are equal. Therefore, ABCD is a rectangle. With this, we have come to an end to chapter 9 circles.